All right, picking up from the last video, we're going to calculate the probability of finding a certain range of sample means. And to do that, we need to use our z-tables and compute the respective z-values to get there. Remember, the z-table and z-values are going to be used anytime we want to find the probability in a normal distribution. That's one of the advantages of having a distribution that is normal, because we can use these tables to quickly determine probabilities. Let's start with the actual z-value for a particular sample. Well, to calculate the z-value for any sample mean in our distribution of sample means, we would find how far that sample mean lies from the population mean, and then divide that by the standard error. It's no different than the z-scores from before. When we were looking at a data set, we would take a particular data point and find out how far that lied from the mean in terms of standard deviations. Well, this is how far our data point, our data here is sample means, how far they lie from the population mean in terms of standard errors. So it's really no different. Let's suppose we have a large population that has a mean of 8, a standard deviation of 3, and assume that we pull a random sample of 36 from that large population. Let's find the probability that the sample mean that we get is between 7.8 and 8.2. To do this, let's lay out some of our numbers. Well, we know that the mean of the sample means is going to be 8. We know that because of the central limit theorem. Remember, the mean of the sample means will equal the mean of the population, and we've been given the mean of the population. Therefore, the mean of the sample means will be 8. We also know from the central limit theorem that the standard error of the sample means will be equal to this. So we simply take the standard deviation of the population, which is given, and we divide that by the square root of our sample size, 36, right? And that's this formula here. If you do that, you get 0.5. So we have the mean of our sample means, and we have the standard error of our sample means. We now know not only the central tendency, but the variability of those means. Because we have a sample that is over 30 or over, it's in fact 36, we can assume that our sample means are distributed normally. Now remember, there were two conditions under which we could do this. We could assume our sample means are distributed normally if we know the population is distributed normally. We don't know that because there's nothing in this narrative to tell us that the population is normal. But because we pulled a sample greater than 30, and because it's from a large population, we met the second requirement. So once we understand that it is normally distributed, we can then use our z-tables to calculate various probabilities. For example, if we want to know the probability of a sample mean between 7.8 and 8.2, we'll just convert these 7.8 and 8.2 values into z-scores and use the table. Let's do that. First off, down here, notice the population distribution. Now, that x implies we're looking at the actual data in the population. We know the mean of the population is 8. That was given to us. We don't know that it's normal. We're kind of drawing it like it's normal, but that's only because we can assume it's normal for the reasons I described before. Next to this, we have our sampling distribution. The sampling distribution will have a mean equal to the population distribution. And what we want is to find the probability of getting a sample mean between 7.8 and 8.2. So we identify 7.8 here and 8.2 here, and then we can shade in the area to say this is the area we want to find in terms of probability. But the x bar values, the means, don't tell us the probability. Z values do. So we need to convert our x bar sample means into standardized z-scores. So we use this formula. Let's start with 8.2. Well, 8.2 minus the mean of 8 is 0.2. And then 0.2 divided by 0.5 is 0.4. So the z-score that corresponds to 8.2 is 0.4. On the other side, 7.8 lies 0.2 from the mean. So we take 7.8 minus 8, which is negative 0.2, divided by the standard error of 0.5 equals negative 0.4. So our z-values are negative 0.4 on the left-hand side and positive 0.4 on the right-hand side. Now let's go to our z-table and actually find the probabilities. What we're looking for is underlined here. It's actually 0.4. So 0.40 if we go to hundreds, and that's 0.6554. Well, recall that when we have a positive z-score, the probability tables tell us the probability of a z-score up to that point, from the left tail all the way up to that point occurring, which means that's capturing this entire area here. The problem is we don't want that entire area here. So what we do is we take that 0.6554, which represents this area, and we subtract this half. Okay? And we're left with just this area here. Okay, so I'm going to do my best to draw this in, but it would be this area here. And that would be 0.1554. Okay? 0.1554. And then if we go to the z-tables to look for the negative 0.4, it's the same z-tables, it's just this is going to be a negative. Same probability, 0.6554, but now we're starting on the right-hand tail and we're moving this way. The negative z-scores tell you the probability of getting a value all the way up here to that negative score. So it's telling you the probability of getting this entire area here, but we don't want this entire area. We only want this, right? We want the other half, right? This to here, like that, okay? And that's going to be 0.1554 because we back out this half here, which is 0.5, right? So the end result is you take 0.1554 representing this area and 0.1554 representing this area, and you get 0.3108, 0.3108. And that is the probability of getting a sample mean between 7.8 and 8.2. In other words, if you have this population that we assume to be normally distributed and you randomly pull a sample of 36, you have a 31% probability of drawing a sample mean between 7.8 and 8.2. That's all it tells us. Okay, moving on, let's practice this in an application. It says, in the following exercises, assume that the sample is taken from a large population. First one, the mean weight of 10-year-old girls is 80 pounds and the standard deviation is 6 pounds. If a sample of 31 girls is selected, what is the probability that the mean of the sample is between 78.5 and 80.5? To do this, let's go ahead and illustrate in our diagram. First off, we need to find our x values, which is x bar because we're looking at the distribution of sample means. Well, we know from the question that the mean weight of 10-year-old girls is 80 pounds, and the mean weight of the population will equal the mean of the sample mean. So we put 80 here as our mean. We also know that the standard deviation of the population, let's put that up here, standard deviation is going to be equal to 6 pounds. Okay? But because we're dealing with the distribution of sample means, it's not the standard deviation that matters, it's the standard error. So it's actually sigma x bar, which is going to be the population standard deviation, right, divided by the square root of our sample size. Okay? And that means we're going to have 6 divided by the square root of our sample size, which is 31 from the question, right? 31 girls were selected. Now, if you do the calculation, you should get 1.07. So let's put that here, 1.07. So now we have not only the mean of our sample means, but we have the standard error of our sample mean. Next, let's add in our range that we want to determine the probability for. In the question, it says find the probability of a mean sample between 78.5 and 80.5. Well, 78.5 is going to be somewhere down here. Right? Put 78.5 here. And then 80.5 is going to be above the mean. So we'll put 80.5 here. Okay. So once we have our range, we can then shade in the area that we want to calculate. I'm going to go ahead and do that with the highlighting tool just to give us a sense of what we're doing here. Again, the illustrations are crude, but hopefully you can follow, and it gives you a sense of the process. All right. Next step is to calculate the z values that correspond to this. We've got our x bars, our sample means, but we actually need to standardize that to z to get the probabilities and use the table. So let's find the z-score that corresponds first to the mean. We know that's 0. But then for 80.5, well, to do that, we need to find out how many standard errors this value lies above this. So we just take the 80.5 and we subtract 80, which is 0.5, and we divide that by our standard error, which is 1.07. And if you do that, you should get 0.47. So this value here is 0.47 standard errors above the mean. What about this one here? Well, same process. We take the 78.5, subtract the mean of 80, and we get negative 1.5. So this value lies 1.5 to the left of the mean, below the mean. And we divide that by the standard error of 1.07, and you get 1.4. That is negative 1.4. Okay. So with this information, we can then use the z-table. Let's first find the 0.47. So for the z-table, we go to 0.4, right, and over to 7, or 7, and it looks like 0.6808. Okay, 0.6808. So that means, because it's a positive z-value, that the entire area from the left tail to here is 0.6808. But we don't want that, right? We only want this area here. So we back out 0.5. And we're left with this area here being 0.1808. Okay? And then we're going to find the negative 1.4. To do this, we go back to our z-table, find 1.4, and we get 0.9192. Well, that means, because it's a negative z-score, that we're starting from this tail. So we have a 0.9192 probability of getting a z-score in this range here. But we don't want that range here. Okay, so we need to take the 0.9192 and back out this half, okay, which leaves us with 0.4192. Okay, now you take the 0.4192, which is this area, and you add to it the 0.1808, which is this area, and you will get a total of 0.6. So this is your answer. The probability of getting a z value between negative 1.4 and 0.47 is 60%. Similarly, the probability of getting a value from 78.5 to 80.5 is the same.